Hi students, this is Mr. Epperson and this video is on mass and density. If you've ever golfed before, you've probably done better than me. I'm not very good, but if you've ever seen golf or seen people play golf, the unfortunate reality of the water trap is that when you hit your really expensive golf ball into it, it sinks down to the bottom. And you probably aren't surprised at that, but it's kind of interesting because in this video I have here of these two different balls that I was testing, one is a ping pong ball and one is a golf ball, but they're both almost exactly the same size. Why does one sink and one floats? Well, if I was to crack it open and cut them, you'd actually see on the inside of one, you would have basically empty space, and on the inside of the other you have kind of like a dense core. And of course that makes sense, right? One of them has sort of like some kind of substance in it so that when you hit it it'll actually go far. The other is meant more for just hitting across a table with the game of ping pong. So they have their uses, but that dense core actually means that the golf ball has a weight to it. Now, if that dense core though was made out of styrofoam, the golf ball would still actually float instead of sink. So what we know about the denseness of the core is that it's about the same density as the water that it's actually floating in. In fact, it's a little bit more dense because it sinks. What we're going to learn today is how we can predict that by some of the aspects of density that we can learn in this course. So I've used that word density. Density is basically made up of two components, mass and volume. So we'll revisit what those two are just briefly. So mass is basically just the amount of stuff that's in an object. That's a very basic definition, but it's a pretty good one because it's a little tough to define. So it's just the stuff that's in an object and the amount of that stuff. It can be measured. So we can measure this using a scale, though there's sort of a limitation to that. We'll talk about it in a moment based on where you are in the universe. But in general, you can get a good value with a scale. And we measure that in the units of grams or kilograms in science class, at least. You might see this even in the kitchen when I'm making my coffee. I see the big G down here at the bottom with how much coffee I'm pouring and water and stuff. So even a kitchen scale will use grams. But you may ask the question, it's a fair question, what is a gram? And how do I understand this unit that we don't really use very often in America? The gram is basically best understood when you can actually hold it. And so if you grab a nickel, you can actually feel how much, well, not really 1 gram weighs. I don't really know what would be a good corollary for 1 gram, but here's an easy way to remember what weighs 5 grams. And it's almost exactly 5 grams. Any nickel you pick up will be almost exactly 5 grams. I've actually measured this one, and it's just within a couple hundredths of 5 grams. It's very, very close to 5 grams. So if you pick up a nickel, it's worth 5 cents and it weighs 5 grams. Like a good way to remember what 5 grams feels like. So what's the difference between mass and weight? Weight basically is different because it depends on gravity. Where you are in the universe matters. Whereas mass is actually independent of gravity. It doesn't matter where you are, you will always have the same mass because it's the stuff that makes you up. So if I was on the planet Mars, maybe I was lucky enough to get on one of the rocket ships that's leaving from SpaceX at some point in the next 10 years or so, and they take me there, I would weigh about 1/3 of my body weight. I would, if I weighed 110 pounds, if I went over there, I would weigh only 42 pounds. So I weigh a lot less on Mars, but I still have the same mass, 50 kilograms, and over there I'd weigh 50 kilograms. I don't weigh 110 pounds, but this was a graphic I got offline. If I went to the moon, I would actually have even less weight. I would weigh about 1/5 of my body weight. So there's pictures of astronauts trying to walk on the moon You can't really walk on the moon very easily, especially in a big suit, but you sort of float along on the moon because the gravity is so little. So that astronaut still has the same mass as when he left the planet, but he has a different weight when he's on the moon. So that's the difference between those two concepts. However, remembering that we're basically, when we say mass and weight in this class, we kind of mean the same thing because we're always on planet Earth when we are talking about this stuff. So unless we ever left the planet, we'd basically be fine using the same words interchangeably, but they are different. Volume we've talked about quite a bit, and that's how much space something takes up. If mass is what it's made out of, the amount of substance, volume is the amount of space. And we can measure this a couple different ways. The units are going to be sort of a little different than something you might be used to, a milliliter or a cubic meter, because it has to be length and width and height, especially if you're dealing with something geometric like a box. You can take a ruler and you can measure all those different dimensions and you can get a volume pretty easily. If you're dealing with something like a ball or a balloon, you have to use a couple different methods to find the volume, but you can do it. It doesn't matter what it is, though. If it's the volume of a liquid or the volume of a solid, you can still use the milliliters unit in order to measure it because it's a unit of volume. It doesn't matter what you're using, what object you're talking about, it still works. So density, going back to this concept, is mass and volume. But how exactly are they related? Well, remember the volume units are milliliters. The units for mass is grams. So what's the units for density? Well, it's just grams divided by milliliters. And if you think about this, this kind of makes sense, right? Because you can basically take the amount of a substance and say how much weight is in that substance based on how much of it I have. It should be the same density no matter how much of that object you have. If you have a whole, golf ball, the entire thing, or only half of it, you should still be able to say that the density of that object is the same. Remember, the golf ball sunk before, and even though I only have half of it, it should still sink if I drop it into the bowl, right? And so I've only got half of it, but the density is half. Shouldn't be half. It should be the same. And there you go. The golf ball does in fact sink. I'll take out this ping pong ball that is not sinking. So even though that's kind of an interesting fact that a ping pong ball, it will only float if you float it like a boat. But if you put it sideways and you fill in that void of air, it will actually kind of sink. So the density does stay the same regardless of whether you've cut something up or not. Unless, of course, you've now allowed air inside where before it was prevented from going in, like in the case of the ping pong ball. Okay, so let's do some practice problems here. Because in chemistry, often what we're doing is calculating densities. Okay, so let's do one where we have something with a mass of 100 grams and a volume of 100 milliliters. Now, all I have to do is divide those two together. So I got 100 divided by 100, and I get 1, right? Well, I get 1 gram, let's keep my units, and 1 milliliter. Typically, as a scientist, what you're supposed to do is just write 1 gram over milliliters. And the reason we do that is because the 1 here is implied. So we don't bother writing that bottom number with the unit. And what that means is that for every gram of a substance you have, you also get 1 milliliter. And vice versa, for every milliliter of a substance you have, this particular substance, you get 1 gram on the scale. Let's try that with another number. How about 25 grams and 100 milliliters? Well, if I do the math here, make it a little bigger, 25 grams and 100 milliliters divided from each other, that's the same as saying 1 over 4, right? Because 25 is a quarter of 100. So 1 over 4 grams per milliliter. And I could do it this way, just reduce the fraction to a decimal, 0.25 grams per milliliter. If I have 1 milliliter of this substance, it's only going to weigh 0.25 grams, a quarter of the weight of this substance up here. So this one would be less dense than this substance. Okay, let's do another one. How about 1,000 grams and 100 milliliters? What's that one going to be? See if you can do it before I do it. Okay, I'm going to let you pause if you haven't done it already. You can do it now, but regardless, here we go. 1,000 grams divided by 100 milliliters is just going to be 10 grams per milliliter, 1 milliliter. And again, we don't really need to write the 1. But that's pretty easy to figure out with math-wise. 1,000 divided by 100 is just 10. You take care of all the zeros, and you're left with 10. But as we can tell, all of these are different densities, but they all took up the same space. They all were 100 milliliters. This one just weighs a lot more than this one does. You can imagine this, right? Like maybe a styrofoam ball and a plastic kind of toy ball and then a bowling ball or something, or maybe like a baseball and a bowling ball. They could all be around the same size, but you would actually have one weighing a lot more than the others. So that's just one way of kind of seeing density and the differences between those numbers, and why some things are in the end going to sink and why some are going to float. So that's the basic overview of density, and I hope that's helpful. So you might be asking yourself the question, what is a gram and where does that come from? It's sort of a foreign unit. Like I understand a foot because it's the size of, my foot basically, or somebody else's foot, but it's the size of a foot. But a gram, where does that come from? Why is that helpful? Why do we use it? Well, people decided long ago that if you wanted to sell something, it's good to know how much that stuff weighs, because if you're selling apples, not all apples are the same size, right? And so you want to make sure if you're getting a price per pound or something like that, you could come up with a way to do that. Of course, they didn't have price per pound yet because they didn't know how to put together weights for things. So what they did was that they would say, if I put my apples over here and I put this object over here, and they balance, this is a movable balance that would kind of move as you put objects on it. If they balance, then that amount of fruit on that side weighs 1 kilogram or some variation of that, whatever I wanted to sell. But let's say it was 1 kilogram. Then I would be able to take that weight right there. I'd be able to take that with me and bring it over to another place and say, all right, I want another kilogram of apples from somebody else. And I would be able to weigh out the same amount, whatever city I'm in. And everyone had the same standard units. Plus, that also means if I want to, buy a kilogram of apples, or if I wanted to buy a kilogram of gold, I can still get the same amount of stuff for the same weight. It doesn't matter what the object is, I can still have the same weight. So kilograms are basically just a counterbalance. You can just put it on the other side of a scale and know that whatever is on that side is going to weigh a kilogram. Of course, people gamed this system and they, hollowed out their kilograms so that they were weighed less and they could end up selling things to people and making more money, and people would do the opposite where they'd be heavier and they could kind of get more. So there are ways that doesn't work, but the beauty of the kilogram is it actually is a kilogram sealed away that is the master kilogram, and all other kilograms can be weighed to this kilogram that's over in Europe. And they're actually retiring it, but it's a standard kilogram that is exactly 1 kilogram, and it is the thing that all other kilogram measurements are weighed against. So that we know that whatever you've got that says a kilogram should have the same weight as that kilogram that's over and locked away in Europe.